So I said I wanted to do another application of the Boltzmann probability distribution. So let's do a little molecular physics now. The water molecule, it vibrates in various ways. One way for it to vibrate is what's called the flexing mode, in which the hydrogen atoms move toward and away from each other, but the hydrogen-oxygen bonds don't stretch in length. Now I'm going to draw a sketch in a minute, but if you think of an oxygen atom down here, bonded to a hydrogen atom here and here, then these bonds are going like that. Okay? All right, we're going to approximate the oscillations to be simple harmonic. Of course we are. We're physicists. Okay? The frequency is 4.8 times 10 to the 13 hertz. You measure that in molecular spectroscopy. Of course, for any quantum simple harmonic oscillator, doesn't matter what it is, the energy levels are the famous E sub s equals s plus a half times hf, where s is a quantum number, starting at 0 and going up by integer steps. And h, of course, is Planck's constant. F is the frequency of the oscillation. Right? This, of course, is one of the things that you must know if you're going to take the physics GRE. The energy levels of the harmonic oscillator. Okay? All right. So we're going to imagine a water molecule in a thermal reservoir. And the energy levels are here. So there are the states. Just each S is a different state. What's the probability of finding the molecule in particular vibrational states? Boltzmann probability distribution will tell you. To use the Boltzmann probability distribution, the first thing you have to do is calculate the partition function for your system. Our system is a vibrating water molecule. So here we go. So our second application of the Boltzmann distribution function is vibrations of a water molecule. So I'm talking about that's the oxygen, the two hydrogens, that represents the bond of each hydrogen atom to the oxygen atom. And we're talking about these bonds oscillating. Now, by the way, the size of these oscillations isn't very big. Okay? But they're oscillating like that. And the frequency that's dominant has this frequency of oscillation is 4.8 times 10 to the 13 hertz. Of course, that's very high, but molecules are very small and they can oscillate rapidly. Okay? So we're going to treat the molecule as a quantum simple harmonic oscillator. That means the energy levels, E either sub s, like that, okay? Or you could write it E of s if you want. Doesn't really matter. Just denoting the energy levels depend on this quantum number s, is the quantum number s plus a half times Planck's constant times the frequency, where the quantum number s starts at 0 and goes up by integer steps. So you can think of each one of these s's as a different vibrational state. Okay? And each vibrational state has a corresponding energy, and obviously the ground state of the vibrational motion is when s equals 0, and the ground state energy is hf over 2. And the first excited state vibrational energy is when s equals 1, that's 3/2 hf, and so forth. So this system is in a thermal reservoir because this is one water molecule in a sample with lots of water molecules. So all the other water molecules are the reservoir. So all I have to know is, well, what's the temperature of this reservoir? Okay? Well, that's what we'll ultimately need to know. But first, we're going to calculate the partition function for the system. Z is the sum over all the microstates. They've got to be labeled somehow. I'm going to use the quantum number S. All the microstates means that S ranges in integer steps from 0 to infinity of the Boltzmann factor, so e to the negative E sub S over kBt. Now I see that I have an infinite sum. My toy model I did with the atom with 3 energy levels, obviously that was a finite sum. And figuring out the partition function was pretty straightforward. Here I have an infinite sum, so we're going to have to see what we can do with that. Okay? Alright, so let's start working on this, because this sum, S going from 0 to infinity, E of, well, let's put in the expression for the energy levels. S plus 1/2 times H times F. And then divide that by kBt. So that's the sum I have to perform, where the explicit dependence on S is right there. To help me do that infinite sum, to try to figure out how I'm going to do that infinite sum, let me just do a little bit of notation to clean this up and to make it easier to see how to do the sum. Okay? So I'm going to let a quantity alpha be defined to be HF over kBt. And as far as this sum is concerned, that's just a combination of constants. Right? So I'm just going to call it alpha. And if I do that, then the expression for the partition function is the sum, S going from 0 to infinity, e to the negative, S plus 1/2 times alpha. But of course, exponentials have wonderful mathematical properties, such as the exponent with its argument with the sum is actually the product of 2 exponents. So this is e to the minus S times alpha times e to the minus alpha over 2. And I can bring the e to the minus alpha over 2 out front, because it doesn't depend on S. So this expression is e to the minus alpha over 2, sum S going from 0 to infinity of e to the minus alpha S. I still have to figure out how to do this sum, but I've tidied it up a bit and it might be able to help me. For example, the next thing I'll do, just for notation again, is let x represent e to the negative alpha. Note then, I know, because alpha is positive, right, that x can range between 0 and 1 like that. Because e to the negative alpha can range between 0 and 1. Okay? So if I do that, my expression for the partition function is e to the negative alpha over 2, sum S going from 0 to infinity of x to the S power. Because e to the minus alpha S is e to the minus alpha to the S power. Right? Because you multiply exponents. Now, I am summing up a quantity to successively higher powers, right? So this looks like this. E to the minus alpha over 2. First term is x to the 0, which is 1. Then plus x to the 1 power. Then x squared and x cubed, dot, 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 to infinity. Notice, this is a very famous series. Adding up terms to successively higher powers, where the base here is a quantity less than 1. Okay? That is a very famous series. You want to be able to recognize it when you see it. Even though it's an infinite series, it's called the geometric series. Okay? Where you're just taking the same quantity, x, that's less than 1, and raising it to successively higher powers. Okay? And that sum converges because the quantity x is less than 1. And there's a famous result for that infinite sum. Don't forget I have the e to the minus alpha over 2 out front. Can't drop that. And the sum for the geometric series is 1 over 1 minus x. So here's a case where even though it's an infinite series, infinite sum, you can sum it. And there's a well-known analytical result. Okay? So now all I got to do, so this is exact. This is the partition function for this vibrational motion. Let me substitute back in, remember the x is e to the minus alpha. So let me substitute that back. Right? E to the minus alpha over 2 over 1 minus e to the minus alpha. Then I'm tempted to work with that a little bit and make it, see if I can make it look prettier. For example, I can multiply numerator and denominator by e to the positive alpha over 2. And then the numerator will become a 1. And the denominator will become e to the positive alpha over 2 minus e to the negative alpha over 2. And then I have to remember yet another useful identity. The hyperbolic sign of a quantity x is e to the x minus e to the negative x over 2. Minus e to the negative x. And I see here that I have in the denominator 2 times the hyperbolic sign of alpha over 2. So my partition function is 1 over 2 times the sinh of alpha over 2. Ah, you can't get much better than that. I will, although, go back and substitute in for the alpha. Remember the alpha was just a notation. HF over KBT. This is 1 over 2 times the sinh of HF over 2 KBT. And I have found the partition function. You could argue, I suppose, that it depends on two things. Whatever the oscillation frequency is for the molecule. But the important thing is the temperature. Because that, I can think of that as a variable, then I can consider any temperature for the reservoir I want. Okay, now that you have the partition function, all the various probabilities of finding the molecule in various vibrational states can be calculated. So the first thing we're going to do for probabilities here under B is calculate the probability of a water molecule being in its flexing ground state and in each of its first 2 excited states, assuming that it is in equilibrium with a reservoir at 300 Kelvin. Okay? Well, that's pretty easy to do. Okay? So we have T equals 300 Kelvin. That's our reservoir temperature. That means, by the way, that I can calculate a value for the quantity I've been labeling alpha, just so you know, because I know H, and I know F, and I know KB, and now I know T. And of course, note, H times F in the numerator has dimensions of energy, and KBT in the denominator has dimensions of energy, so alpha is dimensionless. And the value of alpha when the temperature is 300 Kelvin, these are 3 sig figs, is 7.72, just for your information. And now, I start calculating probabilities. So that would be the probability for the flexing ground state. I would use S equals 0. So that's the Boltzmann factor. E to the minus capital E0 over KBT over the partition function. Well, E0 is HF over 2. So this Boltzmann factor is e to the negative HF over 2 KBT. So one way to write that is e to the negative alpha over 2. And the z, the partition function, well, is 1 over 2 times the sinh of alpha over 2. So this is e to the negative alpha over 2 times 2 times the sinh of alpha over 2. And that's when I would now plug in numbers, because the alpha is 7.72. Okay, so plug in alpha of 7.72. And I'm going to give you a lot of sig figs here. You get a probability of 0.99956. Okay, well, I know that it's pretty much going to be in the ground state. But we'll calculate the first two excited states as well. So that would be the probability that S equals 1. That's e to the minus capital E1 over kBt all over the partition function. Let me just show you, by the way, a nice little compact way I wrote this out so that I didn't have to do a whole bunch of stuff with a calculator. I wrote the numerator as e to the minus 3 alpha over 2 over z then. Then I wrote that as e to the negative alpha times e to the negative alpha over 2 all over z, like that. But the quantity in the parentheses was p of s equals 0. So p of s equals 1 is e to the negative alpha times p of s equals 0. So the probability of being in the first excited flexing state is take the probability of being in the ground state and multiply by this decaying exponential, which would be in this case e to the negative 7.72, which is going to be a pretty small number. And in fact, what you get for this probability is 4.4 times 10 to the negative 4. So 0.00044. Okay? And then P of S equals 2, I'm supposed to do the first two excited states. That's e to the negative capital E2 over kBt all over z. That's e to the negative 5 alpha over 2 all over z. That's e to the negative 2 alpha times e to the negative alpha over 2 all over z. That's e to the negative 2 alpha times the probability of s equals 0. So that's damned even more. 2 you get for your final answer, 2 times 10 to the negative 7. So there are the three answers. Clearly, it's most likely to be in the flexing ground state. Okay, I'm just going to talk you through the last part because that'll change one thing. They increase the temperature of the reservoir. So now the water molecules are in a situation where the surrounding temperature is higher, considerably higher, 700 Kelvin. And do the probability calculations again. Okay? All you're going to do is calculate the new alpha. Right? Because alpha depends on temperature, and we've changed the temperature. From 300 Kelvin to 700 Kelvin. Temperature's downstairs, so the alpha is not going to be as big. The alpha value now is 3.3. Okay? I'll let you try the calculation for yourself. I'll tell you what you get. For the ground state, 0.96312. Still clearly dominant, but not to the extent as it was before. First excited state, 0.03552. Second excited state, 0.00131. You could just keep doing this all day, right? It would get pretty tedious. But, you know, if you're like a hydraulic engineer, maybe this is important that you know this. Okay, so that's another application. So we've had an application in astrophysics, and we've had an application in molecular physics. Now I want to continue developing the theory a little bit. So, what I want to do next is I want to start talking about finding average values. for properties of our system. Because really, we're talking about probabilities. And if our system really is a microsystem, like a hydrogen atom or a water molecule, well, of course you can only talk about probabilities. That's all you can talk about, even if just you do quantum mechanics. It's probabilities. So if you're stuck to just talking about probabilities, you tend to ultimately end up asking, well, what's the average value of something? In quantum mechanics, you call that the expectation value. Okay? When you're in a given state, what's the expectation value of the energy? It's like the average. What's the expectation value of the position? What's the expectation value of the momentum? Okay? So we're going to kind of do that same kind of argument here. So here's how it gets built up. The history and the theory of this can get pretty complicated, I will say. So I'm going to try to always bring us back to just the simple things. Here's what you got to know. Okay? Let's see, I'm actually up to 5 now, right? Average values. So here's what we do. We're going to do a thought experiment. Right? We're going to imagine a set of capital N identically prepared systems, each having the same microstates available to it, E of S. If you want to have something specific in mind, for example, each system is one hydrogen atom. And maybe they've all been prepared in the ground state. And that's how I start in this thought experiment. Okay? All right? That's one point. Another point. Each system has its own reservoir. I'm telling you, this is a thought experiment. Has its own reservoir at a temperature T. Okay? I'm imagining, if you like, a bunch of copies of my system. Each system has its own reservoir, okay, of temperature T. I will just tell you, by the way, such a set of identically prepared systems is called an ensemble. An ensemble. And I can be more specific. In this case, where the ensemble consists of copies of a system in contact with a reservoir of a temperature T, i.e. what's called a thermal reservoir, this is called a canonical ensemble. So I'm imagining N hydrogen atoms. They were all prepared, say, in the ground state, and then they were each put in contact with their own reservoir, and we let them come to thermal equilibrium with the reservoir. Okay? We may have to wait a while for that to happen, but we'll wait. We'll wait long enough. We'll have to figure out how long that is. Don't worry about that. We'll wait long enough so that each of those hydrogen atoms comes to thermal equilibrium with its own reservoir. Okay? And therefore, each of those hydrogen atoms in this ensemble will be in some state. And it may not be the ground state anymore because they've been exchanging energy with their reservoirs. And it's a big ensemble with lots of copies. Okay? Now I'm going to start doing statistics on this ensemble in this thought experiment. So here's the first thing I'm going to ask. Put a star by this because it's Probably the most important thing I'm going to ask. What is the average energy for this ensemble? Let me tell you exactly what I mean by that question. What I mean by the average in this case, because average often can have different meanings. So first the notation, well, energy, but we're going to use, many books do this, an overbar. Overbar means average value. So this means average energy. Okay? How am I going to calculate it for this ensemble? I'm going to do something that I think will be reasonable to you. I'm just going to go down the line in the ensemble, copy after copy. I'm going to say, what's that hydrogen atom's energy? Write it down. What's that one's energy? Write it down. What's that one? What's that? I'll have n energies, yes? I'm going to sum, then, to get the average energy over all the microstates. I'm going to take the energy of that microstate. I'm going to multiply that. I'm going to write it like this. This is the number of atoms in the ensemble that were in the state S. And dividing that by the total of atoms in all the ensemble, that's just the fraction of the atoms in the ensemble that are in state S. That's what this thing is right here. Fraction of... Remember, each hydrogen atom, if you're thinking of it that way, is called a system. So it's the fraction of the systems in the ensemble that are in state S. This is how I'm going to calculate the average energy. I'm going to take the energy of each state multiplied by the fraction of the systems in the ensemble that were in that state, adding them up over all the possible states. Now the next thing I'm going to do is I'm just going to change the notation on that last term. The fraction of systems in the ensemble in state S, I'm just going to call that the probability of finding a system picked at random in state S. The fraction of systems in the ensemble in state S, you can think of it as the probability of finding a system, chosen at random, out of the set, in state S. So now I'm going to write the way to calculate the average energy of the ensemble is to sum over all the microstates, take the energy of each state times the probability of that state. That's important. Okay? That's important. I'll put a star by it. Just to mark it as important. Okay? That's a general way of statistical mechanics. That's a general way pretty much in most physics to calculate the average value of something. Sum over all the possibilities, the energy for that corresponding possibility times the probability of that. Okay? Now, all I do in the canonical approach to statistical mechanics is I say, well, now that you've written it this way, I know what to put for the probability of being in a particular state S. I use the Boltzmann distribution function. Okay? So that's the next thing you do. Okay? So I'll continue in here. In the canonical approach, the probability that the system is in a given state S is the Boltzmann factor for that state over the partition function. Okay? And that's what I'm going to use in that starred equation. While I'm at it though, by the way, might as well get you used to a notation that is absolutely everywhere in physics, and especially in statistical mechanics. And that is the beta notation in statistical mechanics, where the simple beta is defined to be 1 over kBt. Notice then that the quantity beta has dimensions of inverse energy, 1 over energy. And so, the probability in the canonical approach that a system will be in state S is written as e to the negative beta E of S over the partition function. And this is what you will see. If you do a graduate level course in statistical mechanics, depending upon what the textbook is, it's quite possible that within the first couple of pages, this expression will appear. Written like that, where right after it will say, where beta equals 1 over kt. And everywhere else in the rest of the book, you're going to see betas. Okay? It's quicker, for one thing, to write e to the minus beta energy instead of e to the minus energy over kBt. Okay, so with that in mind, let's write down our expression for the average energy of this ensemble of systems. Here we are. E bar is the sum over all the microstates, the energy of each microstate, times the probability of the microstate, which is e to the negative beta times the energy divided by the partition function. But remember, the partition function is basically a normalization constant. It does not depend on this sum over the states here. So you can pull the 1 over z out front. And so you've got 1 over z, sum over the states S, the energy of state S times the Boltzmann factor for state S. And I'm just going to label that as, I'm going to be a little bit generic in my labeling, average energy of system. Definitely want to number that equation. This will be used quite a bit. Okay. Now here's something you could ask anyways, or you could at least find. Since the ensemble consists of n systems, right? My ensemble consists of n copies of the system. So, since the ensemble consists of n systems, the total average energy of the ensemble can be written out using equation 1. Here's the notation I will use. The total energy of the ensemble, I'm going to use capital U, like your author would use for total energy. And I just take the average energy calculated using this approach of a system, and I multiply it by the n copies that I have. So n times E bar. That's equation 2. The total average energy of the ensemble is n times E bar. Now I am going to do a kind of change of perspective, I suppose you might say. I'll put a star by this. What's that? Oh, okay. All right, I'm going to take a slight change of perspective, and I'm going to kind of get, I use this ensemble way of thinking to get to equation 1 and 2. Equation 1 and equation 2. I just needed to get to those using what is presumably correct thinking. Okay? It's just equations 1 and 2 I need. I am going to now slightly change the interpretation of equation 2. Okay? Here we go. Suppose we have n objects, for example, n atoms, in contact with one thermal reservoir. So I'm not talking about n copies of a system and a reservoir. Just N atoms, really, they themselves are the one thermal reservoir, right? Any one atom is surrounded by all the others, and all the others make up the reservoir. Okay? But I have N objects in contact with one thermal reservoir. Here's the claim. That the average, well, I'll do it in the same order I wrote it there. The total average energy of the N objects is N times E bar, i.e. equation 2. Right? Just use equation 2. So the whole ensemble idea is really just to help you get this line, so that you can see how to calculate the average energy. You say, okay, if I have all these copies, it's easy to figure it out. I just multiply the energy of a state by the fraction of the systems in the ensemble that are in that state. And that's really what I needed the ensemble idea to help me clarify, was what to put there. And once I had that, I don't really need the ensemble idea anymore. So we're going to use this a lot. Okay? Notice what I've got then. If I've got a system, if I've got a collection of N objects like N atoms or N water molecules, okay, then the way I'm going to get the total average energy is I'm going to find the ensemble average, E bar, use equation 1 for that, and I'm going to multiply by N, the number of objects. Then I will have the total energy of that set of N objects, but technically it will be the average energy. Okay? So now that leads me to the next idea. Fluctuations in energy. So, in real time, the total energy of an N object system fluctuates about the average value N times E bar. That's an important point. Okay. In real time, just watching the set of N objects and keeping track, assuming there's a way to do it, think of this as a thought experiment, keeping track of the total energy of the N objects as time goes on, well, you'll see rather random, irregular fluctuations about this average. So, how important is the average then? Depends on how big the fluctuations are. If the fluctuations are big compared to the average, then the average isn't very helpful. But if the fluctuations are small compared to the average, then really, and hopefully really small compared to the average, then all you got to do is take that and say you're done. So it's important to quantify how big these fluctuations are. Okay? So how large are these energy fluctuations? That's an important question, theoretically. How large are these energy fluctuations? I'll get a little bit of that set up here. How are we going to answer that? We've got to quantify that somehow. Well, actually, perhaps surprising or not, I don't know, but we're going to use an idea that is in essence introphysics or introstats. If I have a sample of numbers and I want to quantify how much spread there is in a sample, we have ways to do that just in statistics, yes? You ever hear something called a standard deviation? the measure of the spread. That's what we're going to use. Okay? But what we'll do is we'll actually start with the standard deviation squared. Everybody know what that's called? It's called the variance. Okay? So we're going to calculate the variance of the energy of our n objects system. Using the definition of variance from intro stats, okay, like this. We'll use the symbol sigma sub e squared for the variance of the energy. You can calculate the variance of any measurable property. Any measurable property. Right? So the subscript will be whatever is the variance of. Are they length measurements? Are they energy measurements? Are they momentum measurements? Right? So you'll always put a subscript to know what kind of thing is being measured. And sigma actually represents the standard deviation. Sigma squared is the variance. How do you calculate? Well, the square of the standard deviation. We're going to sum. I'm going to use an index I now, going from 1 to n, because I'm going to go for each object one at a time. And I'm going to take the energy of the object, E sub I, minus the average energy for the set, and square that, and add all those up, and divide by n. That's what I mean by variance.
Does it apply the whole summation by n or the inside?
Doesn't matter. Right? Yeah. You can put the 1 over n out front if you want. We can do that. Why don't we do that? 1 over n. Okay. Now I want to show you a little bit how you can work on this. Get a little bit down here. Let me expand this square. Sum I going from 1 to n of the energy of object I squared minus 2 times the average energy times the energy of object I plus the average energy squared. Close parentheses. I'm trying to write that very carefully. Watch very carefully how I wrote that and write it exactly like that. Now let me break this up into a series of terms. Yes, because the sum of a sum, right, I can distribute it through. So the first term is this, 1 over n, sum I going from 1 to n, ei squared. That's the first term. In the next term, notice it's got a minus. I'll put constants out front. Constants mean anything that don't depend on the summation index, I. Okay? So in this term, do you see what does not depend on the summation index I? Obviously the 2. And the E average. It's just a constant, right? So there'll be 2 E average times 1 over n, sum I going from 1 to n of E sub I. Yes? And then look what I'll have last. Plus E average squared times 1 over n, sum I going from 1 to n of 1. You see what I did? The last term? That E average squared is a constant. It can be pulled out front of the sum, then I'm just summing up the value 1. Alright, one more step and then we'll stop for now. Okay? So, the variance in the energy for this n object sample. Alright. Anybody recognize what this sum would give you in the end? No, I'm not asking you for a number, but just what quantity is this calculating? 1 over the number of objects, sum over the objects, take the energy squared of each object. What is that going to be conceptually? What is that calculating? Average of what? Not the average of the energy, because that would have just an E here, EI, not an EI squared. So it's the average of the energy squared. You're averaging the energy squared for each object, yes? You can average any property you want, right? Here, this is averaging the energy squared. So the way you would denote that, look carefully, is you write E squared, and you put the bar all the way across, including over the 2. Understand why I'm hitting that statement hard? This means the average of the energy squared. Now let's keep going. Minus. All right, I've got a 2 times just the average energy. Now look at this sum. Can you tell me what that is conceptually? It's the average of the energy, right? So this is another factor of the average energy. Plus the average energy squared. Look carefully at the line and the square exponent there. There's a 1 over n, but what is this sum going to give me? What do I get when I add up 1 in this sum? What do I get when I add up 1 n times? N, right? So this sum just gives me an n. But there's an n downstairs. So those cancel. So all I'm left with is the E average squared. Now look at this. This is E squared average minus 2 E average squared minus E average squared.
Is it plus?
Yeah, yes, it's plus. Very good. Absolutely, it's plus. Okay? But that simplifies, yes? This is E squared average minus E average squared. You got to be really careful with the bars and the 2's. All right, this gets numbered. That's what we're going to use. And so that's a good place to pause. That's a quick way, well, it doesn't have to be quick, but it's a compact way to write the formula for getting the variance of the energy in your set of n objects. You average the energy squared for all the objects, and completely separate from that, you average the energy for all the objects. Then you take the average of the energy squared minus the average of the energy squared. Right? And these are not the same thing. Not at all. And that difference turns out to be the variance. That's going to tell us how big these energy fluctuations are. That's going to tell us how important that is. Okay? Alright, so that's where we're going to pick up on